I'm Erkin and this is Patricia, and today we're going to be talking about our deep learning project. So our project is introducing an alternative vehicle detection model by using a deep learning approach as an alternative to the linear support vector machine, SVM, and HOG approach, which is a traditional machine learning method for vehicle and lane detection. Our project is to leverage convolutional neural networks to recognize vehicles for the autonomous vehicle applications. For this project, we used datasets provided by Udacity's self-driving car NanoDRIKI program, which consisted of vehicle images as well as non-vehicle images. We tried out many different architectures to come up with our final model. So our dataset, the total number of samples in the dataset are 17,760, and each image is colored having a resolution of 60 by 64 pixels. This is a binary classification project with two classes, cars and non-cars. As you can see, the cars have a label of 1, whereas the non-cars have a label of 0. As we look at the distribution to the dataset of our dataset, we can see that it is quite balanced, which would prevent any biasing of the data. Moving to our model construction, we initially started with the LearNet 5 architecture. However, the maximum accuracy we could obtain was around 96%, so we decided to implement a different neural network architecture. We then decided to use the VGG16 architecture. However, due to its complex and computationally heavy structures, we decided to come up with our own CNN configuration. And we used dropout to minimize the risk of overfitting too. We then borrowed the technique used by Max Ritter, which evolved from the fact that this is a binary classification problem. And the idea was to construct a model that we input 60 by 64 small training samples and one single future convolutional layer of size 1 by 1 at top. And the output of this top layer would be used as a probability value for classification. And we named our model URBANET. Our model architecture consists of 4 convolutional layers and max pooling on the last convolutional layer. One of the reasons why we wanted to keep our model rather simple was to minimize dropout and computational costs. We trained our model for 20 epochs and reached a training accuracy of 98.6%, as you can see here, and a validation accuracy of 98.6% too. And as you can see, our training loss is decreasing here, and our accuracy has increased. After training our dataset for 20 epochs with our convolutional neural network model, we used this model to make a prediction on a random sample. And the model's prediction for the non-car image was very small. It was 2.9 times 10 to the power minus 17, which was very close to 0. So this showed that our model is very accurate.
So next was to feed a full test image into our network and search for cars in the image to create bounding boxes. The initial step was to obtain the region of interest, which is basically taking out the top portion of the image that has no value to us. And after determining the region of interest, we produced a detection map using our trained model. So since there were no fully connected neurons at the end, and instead there was just a convolutional layer with max pooling and dropout, we were able to use the same network we trained with our 64 by 64 images to detect cars everywhere in the frame, which was really great. So after producing the detection map, the next step was to label detection areas to outline the boundaries of labels. Next step, we're projecting the featured labels of detection points to the coordinate space of the original image, transforming each point into a 64 by 64 square and keeping those squares within the featured area bound. So just in case there might be some false positives, we created a heat map using the overlapping squares and added some thresholds to it. Then we drew a bounding box for every detected heat source. The final step was to get the actual bounding boxes for the vehicles using the function provided in OpenCV. So about the lane detection part, the lane detection part also started with applying a region of interest to the image, which prevents redundant calculation of areas without lanes or anything we might be interested in. The next step, we apply a perspective transformation to better detect the lanes. We then used an HSV color mask to detect white and yellow lanes and combined them with a subtle filter to better detect the edges. After completing the image processing part of our project, finally we wanted to process our project video and to see how well our model performs with real-time detection at 30 frames per second. So the conclusion is that overall our trained model performed well and reached a training accuracy and validation accuracy of 98.6%. There was some overfitting, however, this did not hurt the model's stability to predict accurately. Our model overall performed good in doing real-time detection of 30 frames per second. Further implementation to this project could be used. Could use the VGG16 structure for better accuracy. So here you can see is our lane detection real-time trained, and I'm just going to continue talking about the rest of the conclusion. So we can also use another extension called the YOLO version 2 architecture to perform faster localization and classification of objects. So it was a really great experience to use Keras and TensorFlow, and this project reinforced our knowledge and intuition about deep learning. So thank you for listening.
As you can see, our model is pretty good at detecting objects, and the lane detection turned out to be pretty good as well.
Yeah. So enjoy the video, and thank you for listening.